All right, welcome back to topic 1.4 on relative motion and frames of reference. So, today we're essentially just going to be exploring cases where objects are actually moving with constant velocity. And so, essentially, what we're trying to do is like if one person sees an object moving at some speed, right, then the question essentially is, right, how fast does a second object that could be moving, how fast does that second object maybe see the first object moving, right? So what you can see on the screen here is we've actually got three different objects, right? They can be, let's say that they're cars, car A, car B, car C, right? Car A is moving to the right at 45 meters per second, car B is moving to the right at 30, and car C is moving to the left at 30 meters per second. All of those velocities are defined by somebody, right? Every velocity value, every position, everything really, right? Especially velocity and position, right? Those are the two big ones, and we typically only focus on velocity for this course, as far as I can tell, right? They're all relative to somebody. Somebody is looking at those and saying they look like they're moving 30 or 45 meters per second from my point of view, right? So if we look at all three of those cars, those might be the speeds that we see. But maybe car A looks at car B. Well, car A is not going to see car B moving at 30 meters per second. They're going to see something else. And then likewise for car B looking at car C, right? Car B looking at car A, car C looking at car A, right? All of these different cars are going to look at each other, and they're going to say that our velocity values are wrong, right? Because all of these velocities that we say, they're all things that we're observing, right? And depending on how fast you move, right, what you see is going to be different from somebody who's standing still. And you can think about this when you're going down the highway, right? If you decide to pass somebody, it's going to look like they're going backwards from your point of view. Now we all know that we are still moving, right? We know, we've had enough experience with the world to know that we are still moving, right? And it's not that we're stationary and those people are going backwards, but rather we're both going forwards at different speeds, right? We just happen to be going faster than them. But questions that arise out of this sort of topic, right, are essentially just like how fast does car A see car B going? How fast does car A see car C going? Right, et cetera, et cetera. So we want to be able to figure that out, right? We want to make sure that we're getting the correct notation out of this as well. It's not too bad for one-dimensional motion. Two-dimensional motion, it gets a little bit tedious. So essentially, we're going to take a look at a scenario for both of these. We'll start with one dimension because that's easier. So if we wanted to calculate essentially like relative velocity, as it's called, right? So how fast one object might be moving relative to another, essentially all you have to actually do is just subtract their velocities. So it's actually quite an easy little thing. So let's say, for example, that we're stationary. We see car A moving 45, B and C are both moving 30, but in opposite directions, right? The first question, and I think I'm just going to kind of type this out so I can show you via some examples, right? Is how fast do cars B and C look like they are traveling to car A? So that's going to be our first question. How fast do cars B and C look like they're traveling to car A? How fast does car A see them both traveling? Great, and it is not letting me resize that text box, which is fun. So I'm just going to put it down there, and all right, there we go. Okay, I don't exactly know why my computer's not really working too well today. I apologize. It was working fine last time I recorded. So, all right. Anyway, let's start with car B then. How fast does car B look like it is moving to? How fast does car A feel that car B is moving? Right. How fast does car B look relative to car A? That's another way of saying it. Loads of ways you could phrase that. So, how do we calculate that? Well, car B's relative velocity, right, is going to be given by taking the difference between car B's velocity that we see and car A's velocity that we see, because we're kind of like the control, if you will. We're kind of like the baseline for velocities because we're stationary relative to ourselves, of course. All velocity values are relative, but don't lose too much sleep over like what each velocity value is relative to. You're I can't imagine that College Board is going to ask too many questions about this topic. They, at least in the past, like before the 2025 exams, they typically haven't. But it's also not really actually been its own topic in the course and exam description before. So I'm more so just covering it to cover all of our bases, make sure that we have an exhaustive list of videos for their topic. And I do know that some relative velocity problems do appear on their practice questions as well. So, we'll take a look at that. Anyway, from our point of view, car B is moving 30 to the right, so that's positive 30. Car A is moving at 45 to the right, so that's going to be a positive 45. Well, 30 minus 45 gives us negative 15 meters per second. And that makes sense. What this is telling us is that car A looks at car B and they see car B moving backwards to the left, right? From our point of view to the left, right? But from car A's point of view, it would just be they're moving less in car A's direction. They're moving backwards compared to car A. They're moving backwards compared to car A at 15 meters per second. And that does kind of match what we would expect. Car B would not look like it's going as fast to car A because car A and car B, the difference in their speeds, right, is not as big as the difference between our speed and car B's speed. We see car B going 30, but we're also stationary, right? That's a difference of 30, of course. The difference between A and B is 15, right? Negative 15 at that. So that's why it looks like it's going slower. All right. What about car C? I think I'm actually just going to type this one out because it goes a little bit smoother and faster. So please excuse my not so great notation here, right? These should all be vectors. Car C is all we have to do. Take car C's velocity and subtract car A's velocity from it. And so in terms of that, car C is moving from our point of view negative 30 because it's going to the left. Car A, of course, is still going 45 to the right. So negative 30 minus 45 gives you negative 75 meters per second. In other words, car A sees car C going negative 75. In other words, relative to car A, C is going backwards, which makes sense because they're going opposite directions, and it is going backwards very fast. And that also makes sense because if A and C were to crash, that would be quite a bit of damage. But if A and B were to crash, it would not be as much damage because they're both going the same direction. They have a lower relative velocity compared to each other. So that does beg one question for us then, and we're not going to do all of these, right? You can check some of the other ones, right? Check that maybe car C is going at negative 60 meters per second from car B's point of view. Right, the one I want to take a look at right now, though, is I want to take a look at how fast both C and B see A going. So how fast does car B see car A going? Right, what is car A's relative velocity in B's frame of reference? Another way to word that. Well, that's going to be given by taking car A's velocity and subtracting car B's velocity. So it's actually just the opposite of what we did in our first question. So VA minus VB, and that's going to give us a positive 15. So what car B sees, there's a lot of letters here, and saying the word C doesn't really help that. What car B observes, there we go, is car A is going forward, right? Because it's moving faster in our frame of reference. That makes sense. And it's going at 15 meters per second. Note that they have opposite signs, right? So B sees A going forward, A sees B is going backwards, right? That makes sense based on what you might observe if you're on the freeway and you're one of those two cars. Let's do one more. How fast does car C observe car A to be going? Yeah, I like that wording a lot better. All right. Okay. Scroll down a little bit. No, come on. There we go. So let's do the same sort of thing. Let's do A's velocity minus C's velocity. VA minus VC. If you do that, what you're going to get is 45 plus 30 because C again is going at negative 30. So you're going to get a positive 75 meters per second. Now, here's the confusing part is that the answers to both of our last two questions are both positive, but but relative to car C, A is actually also going backwards, right? If you're car C and you crane your neck, right, you turn your head and you look at car A, right, you're going to see car A going backwards, right? It's going to just keep going farther and farther away from your car's back, right? But it's never going to go in front of you. So it gets a little bit confusing, right? Here, what you can see is that if you have, in other words, if you have negative relative velocities, right? If you have negative results here, that means that you have a velocity pointing to the left. Whereas if you have positive velocities, that means that your object is moving to the right. And so you also have to keep in mind how your original object was moving, right? There are other possible notations out there, but I think that this is probably the best one to follow. I think this is the one that College Board's going to follow. Just, you know, if relative to car C, for example, again, car A is moving to the right, from our point of view, right, then it would make sense for the relative velocity to be positive. So there's our one-dimensional problem. Let's go ahead and take a look at a 2D problem. And I've gone ahead and actually gotten one typed out right here. So there's actually loads of 2D problems you could take a look at. Planes, for example, right? A plane has some ground velocity, right? So that's how that's essentially like how fast it should be going, right? And then, you know, wind, of course, is going to affect the plane's trajectory. And so the plane's going to go a little bit different direction. Let me draw you a diagram so you can see that, independent of what you see with cars A and B right here. We'll come back to that. So let's say, for example, the ground speed of a plane, right? Maybe the plane is going due north at some amount of speed, right? But it experiences a wind. There's wind as well. So let's represent the wind by a red arrow. Well, if the wind is pointing, say, to the east, right, and maybe it's not super strong, but it's kind of strong, let's draw it like that, then the plane's actual velocity is going to be the blue arrow here. It's going to be the vector addition of its ground velocity and the wind as well. So then you can calculate the plane's actual velocity, what direction it's going, and how fast it's actually going then. So that's kind of a cool little application of relative motion. One type of question that you guys are likely going to get, I believe that I've seen this as one of College Board's like practice questions. I don't really have too many of those right now. But is you have two cars. So let's go back to the picture on the right. You have two cars, A and B. A is going due north at 12 meters per second. B is going due east at 5 meters per second. And the question that we're going to do, and you know, you can do the opposite if you want to, check it and make sure that this makes sense to you, right? How fast, or what is car A's relative velocity compared to car B? So in B's frame of reference. All right, there we go. Kind of a nice little one to take a look at, right? What is car A's velocity? What does car B observe car A to be doing, right? What is car A's velocity relative to car B? So in B's frame of reference. How do we do that? Same as we did in one dimension. We do need to subtract. Now be careful here though, because vectors have multiple components. So let's actually rewrite their velocities in our I hat j hat notation, right? So the velocity of object A from our perspective is going to be 0 I hat, right? Because it's not moving horizontally, plus 12 j hat because it is moving vertically. The velocity of car B is going to be 5 I hat plus 0 j hat because it's not moving vertically. So 5 I hat plus 0 j hat. You do not have to write the zeros if you don't want to. The only reason I'm doing it right now is just to make clear what the vector subtraction is going to look like here as we're actually solving it. So the car A's observed velocity from car B's point of view, again, is VA minus VB, right? So VA minus VB, right? Now, keep in mind that because this is vector addition or vector subtraction, right? You have to work with the components independently of each other. So therefore, we would subtract the two j hat terms. That would remain the vertical component of the relative velocity. You would take the difference of the I hat terms, and that would be the horizontal component of the relative velocity. Right, so 0 minus 5 for the I hat terms gives you negative 5 I hat. And you can probably see why I chose 5 and 12 for my velocities now, just to make it a little bit nicer, plus 12 j hat. In other words, what car B's observing is that car A is still going up, right? It's still going due north, but it's also actually going west from car A. That makes sense because if you're car B and you're just going east and you look out, right, and just imagine this kind of as one dimension again, even, right? If you're driving to the east and you look out and you see a tree, right, that tree is going to look like it's going to your to the west from your frame of reference. The same thing's happening here. You have to keep in mind that the horizontal vertical components of vectors are independent of each other, and that carries over to all two-dimensional motion, of course. And so therefore B sees A is going north and to the and or in other words away from it, right, and to the west, right, behind it. It's going backwards essentially. Let's actually find the magnitude and direction though. The magnitude of that relative velocity, and all of these should actually have vector signs here, except for the magnitude when we're getting it. So the magnitude is going to be given by the square root of the x component squared plus y component squared, right? Pythagorean theorem. Square root of 25 plus 144. You can check it if you want to, but that gives you 13 when you take the square root. That's why I chose the numbers, is because it gives me something that I can do in my head. So, all right, there we go. But apparently not something my laptop can do all that fast. But hey, speed's relative, right? Relative to some other laptop out here, my laptop is going at a decent speed, right? So, all right, I apologize. That's like taking so long to write this. I have to be kind of careful because if I try to write it fast, it's just going to cut off some parts of the letters. So, please bear with me. All right, there's our magnitude of the relative velocity. To find the direction, well, we know that A is going up and to the left. So what I'm going to do is when I'm finding my direction, I'm going to define it from the negative x-axis. That way, when I do an arctangent function, it's going to be a little bit easier. So here's A's relative velocity, right? It's got an opposite of 12 and an adjacent of 5. So when you actually calculate that, you should get that this angle of theta, wow, it's lagging so much I can't even write theta. If you take arctangent of 12 over 5, though, that's going to give you 53 degrees. So the relative velocity would be 53 degrees north of west then, based on this. So 12 again is the vertical, the opposite of this angle. 5 is the adjacent. Arctangent of 12 over 5 should give you 53 if I'm doing my math correctly in my head. So there's a couple of examples, right? What I invite you to do would maybe be to check what B's velocity is relative to car A, right? That could be kind of like a nice little thing to take a look at then as well. What you should find is you should find that it would just be the complete opposite of what we just got. So it should still be 13, but it should be 53 degrees south of east then in that point. All right, so I think that's it for relative velocity. If there are any questions that you have, of course, that pop up, or anything that's like very different from what we covered, feel free to let me know, and I'll try to do my best to cover that as well too. But thank you guys so much for watching. One more section, and then we are going to be done with kinematics and moving to forces. So have a good rest of your day, and I'll see you guys in the next video.